Okay, 7.4, the dot product of algebraic vectors. In section 7.3, we found the dot product of two geometric vectors. Now we will discover the dot product of two algebraic vectors when the vectors are expressed as, for example, vector A equals -1, 4, 5. Okay, so that A, B, C, or X, Y, Z form. Okay, defining the dot product of algebraic vectors. So here's the theorem. In R squared, so like that's 2D, if vector A is A1, A2, and vector B is B1, B2, what we do is when we do vector A dot vector B, that's going to be equivalent to vector B dot vector A. Okay, so you can switch these two around and it's going to be equivalent. It also is equivalent to A1, B1 plus A2, B2. Okay, what that looks like is the x's multiplied by one another plus the y's multiplied by one another. Okay, and we also saw in the previous lesson the magnitude of vector A times magnitude of vector B cos theta. Okay, so we saw that in much of this in the last lesson. Now, here's the expansion when we have different components, right? That component form. So in R cubed, if our vector A is now A1, A2, A3, so now we have that Z value, and our vector B is B1, B2, B3. Again, we're extending this to 3D. Then, again, A dot B is going to be equivalent to B dot A. That holds no matter what. That holds if we're in 2D or 3D. Then what's going on here is we multiply the x terms plus we multiply the y terms plus we multiply the z terms. Okay, and then these two are also equivalent. Magnitude of vector A times magnitude of vector B cos theta. Okay, so this box is just all of our equations and how they're interchangeable. Okay, so the quantity of the dot product is calculated by multiplying corresponding components and adding them. Each of the components multiplies to a real number, so their sum is also a real number. The properties of the dot product hold for both geometric and algebraic vectors, okay? We see this because today's lesson, which is on algebraic vectors, is very similar to our lesson on geometric vectors. Okay, same properties hold. And two non-zero vectors, A and B, are perpendicular if A dot B equals 0. Okay, again, that's cos 90, that's going to equal 0. So therefore, magnitude of vector A times magnitude of vector B times essentially 0 is also going to equal 0. For two non-zero vectors A and B, where theta is the angle between the vectors, we get this. We get cos theta equals A dot B over magnitude of A times the magnitude of B. Okay? Where do we get that from? Well, we had the original definition, A dot B is going to be equal to magnitude of A times magnitude of B cos theta. All that is rearranging this equation. So all that is dividing both sides by the magnitude of A, magnitude of B, and isolating for cos theta. Okay, so take a look at this diagram here. The formula for the angle between two vectors. So remember, when two vectors are placed tail to tail, this is our angle that we're dealing with. So cos of this angle, which is tail to tail, equals the A dot B over the magnitude of A times the magnitude of B. Okay, example 1 is a proof. So prove that the distributive property holds for dot products in R cubed. Okay, so what this means is that A dot B plus A dot C is going to equal the same as vector A dot vector B plus vector C. Okay, so first what I'm going to do is I'm going to define, and I'm going to define this on the side. I'm going to define vector A, and it's going to be A1, A2, A3. I'm going to define vector B, and I'm going to define vector C. Same thing, B1, B2, B3. Okay, and then C1, C2, C3. Okay, so how can we prove this? Well, we're just going to sub this straight in to this dot product. So we're going to have vector A, which is going to be A1, A2, A3. And then in brackets, it's going to be dot. We're going to actually add vectors B plus vector C. So we're going to add B1, B2, and B3 plus, it's going to be big brackets, okay, vector C, which is C1, C2, C3. Okay, and we're going to leave the right-hand side for now. So I'm just going to copy down the A1, A2, A3, and I'm going to leave that for a second. Now, we're going to do brackets first because of bed mass. So in this bracket, what we're going to do when we add vector B and vector C is we're going to have B1 plus C1. Okay, comma, we're going to have B2 plus C2. Okay, comma, B3 plus C3. Okay, now what we're going to do is we're going to take the dot product of this. So for the dot product, we want to multiply A1, and then this is going to be multiplied by the first component of the second vector, which is B1 plus C1. Okay, then we're going to go plus A2 multiplied by B2 plus C2. Okay, and then A3 multiplied by B3 plus C3. So in total, when we expand this, my vector is going to be A1, B1 plus A1, C1 plus A2, B2 plus A2, C2 plus A3, B3 plus A3, C3. That is the expansion of the left-hand side. Now I'm going to expand the right-hand side, but in red. I may delete this just so I can get some room here, okay? So what we're doing first is we're going to multiply there we go. We're going to do the dot product of A dot B, and then we're going to add A dot C. So vector A is going to be A1, A2, A3. And we're going to dot vector B, which is B1, B2, B3. Okay, then what we're going to do is we're going to take vector A again, A1, A2, A3. And we're going to do the dot product with vector C, C1, C2, C3. So let's go ahead and multiply each component. So we have A1, B1 plus A2, B2 plus A3, B3. Okay. Then we're going to do the dot product of the second two. So we're going to do a big plus sign that just comes down. And we're going to do the dot product of A dot C. So we have A1, C1 plus component A2, C2 plus A3, C3. And if we bring this entire thing down, this was just like less steps. If we compare them, we can determine that we have A1, B1 in both. A2, B2 is here. A3, B3 is here. A1C1 is here, A2C2 is here, and then A3C3 is here. These are indeed equivalent. Okay, so the distributive property holds for dot products in R cubed. Example 2, given the vectors A and B, calculate A dot B. Okay, so if you think about the definition of A dot B, what we're going to do is we're going to multiply the components of A and B. Okay, so if we have -1, 2, 4 dot 3, 4, 3, what we're going to do is we're going to do -1 times 3. And I'm going to write this out for this question. Then we're going to go 2 times 4. And then 4 times 3. And in between all of these, we're going to add them. So we go ahead and multiply each of these. So we have -3 plus 8 plus 12. So -3 plus 8 is 5 plus 12 is 17. Okay, notice that this is a scalar. So two vectors are going to punch out a scalar for the dot product. Okay, so this was A. Now B is calculate to the nearest degree the angle between vector A and vector V. Okay, so if we think about cos theta equals A dot B over the magnitude of A times the magnitude of B. The two values that we're missing, so we have the entire numerator, it's just 17. The values that we're missing is the magnitude of vector A. So let's go to maybe the side of our paper, and let's go the magnitude of vector A is going to be, okay, square root of -1 squared plus 2 squared plus 4 squared. Okay, each of these components squared, and then we square root it. So we get 1 plus 4 plus 16. Okay, so we get root 21. So we can take this as it is and plug it straight into here. We can express it as a root. Now, magnitude of vector B, we have 3, 4, 3. Okay, so it's going to be the square root of 3 squared plus 4 squared plus 3 squared. Okay, 3, 4, 3. We get 9 plus 16 plus 9. So we get root 34. So the magnitude of vector B, we can then substitute in right here, 34. Then we'll work down our page. I just wanted to show you what we had so far and then what we needed. Okay, so the 17 we're going to keep in the numerator. And in the denominator, because these both are roots, we can multiply them and we get root 714. Our question is calculate to the nearest degree the angle between vector A and vector B. So we're not done because we need this actual angle. So if I put 17 over root 714 in my calculator, I get 0.63620901. And then what I'll do is I'll cos inverse both sides. And I get 50 degrees. So the angle between vector A and vector B here is 50 degrees. Example 3, for what values of K are vectors A and B perpendicular? Okay, so if you remember, perpendicular vectors have a dot product of 0. So what we're going to do is we're going to do A dot B, vector A dot vector B. So vector A is -1, 3, -4. And we're going to dot 3k, -2. So what we want to do is we want to take the components and multiply them. So -1 times 3 plus 3 times k plus -4 times -2. Okay, and this equation is going to equal 0. So -1 times 3 is -3 plus 3k, and -4 times -2 is 8. So that's plus 8. Okay, so 8 minus 3 is going to be 5 plus 3k. We can bring over the 5, and then this is just isolating for k. Okay, divide by 3, k equals -5 over 3. So when this k value up here is -5 over 3, these two vectors are going to be perpendicular, and that means that they're going to yield a dot product of 0. Now, B is the same idea. For what values of M are the vectors x and y perpendicular? So let's do x dot y. So vector x is m, -3 dot vector y is m, -3, 6. Okay, so what we're going to do is we're going to do m times m, which is the x components, plus m times -3 plus -3 times 6. And this is going to equal 0 because we want it to be perpendicular. So m times m, we get m squared minus 3m, and then that's going to be -18. So as soon as we see a trinomial with an m squared and an m, we're thinking immediately that we have to factor. Okay, so what two numbers multiply to -18 and add to -3? Okay, factors of 18 are 1 and 18, 2 and 9, 3 and 6. So if we had a -6 and a +3, those two numbers will multiply to -18 and add to -3. So we're going to go m plus 3 and m minus 6. Those are going to be the two factors. So there's two situations where these two vectors are going to be perpendicular. And that's at m equals -3 and m equals 6. So a parallelogram has its sides determined by vector A and vector B. Okay, so I'm just going to draw that for now. So vector A would be here, and vector B would be here. Okay, when we're talking about a parallelogram, this would also be vector A, and then this would also be vector B. Okay, so those are the sides. Now, determine the angle between the diagonals of the parallelogram formed by these vectors. So if we were thinking about the diagonals, we're thinking this vector here. We're thinking this being the resultant. So that would simply be vector A plus vector B. Okay, so vector A plus vector B will be one of the diagonals. Okay, now the other diagonal, which is like this, as you can see, that diagonal would be from, see this again, so vector A, vector B. If we were talking about this one being the diagonal, if you remember how we take this, like for example, this angle when it's tail to tail, is this would be actually vector A minus vector B. And then we would just take it tail to tail. Okay, because what this does is this is vector A, vector B flips around, so negative vector B, and then we're tip to tail, and then this is going to be the resultant here. Okay, so vector A plus vector B and vector A minus vector B are the two diagonals. So let's actually solve for vector A plus vector B. So we're going to have 6, 1 plus -1, 3. And when we add two vectors, we add the components. We're going to add 6 plus -1, and then comma 1 plus 3. Okay, so adding two vectors is going to yield a vector, and we're going to get 5, 4. Okay, now vector A minus vector B. So we're going to have 6, 1 minus -1, 3. So we're going to go 6 minus -1, comma 1 minus 3. So I get 7, -2. So now that we have this diagonal, we have a vector to express this diagonal and a vector to express this diagonal. What we want to do is we want to solve for the angle between them. So what we want to do is simply do cos theta equals vector A dot vector B all over the magnitude of vector A times the magnitude of vector B. Okay, so A dot B is going to be 5 times 7 plus 4 times -2. Okay, I'm going to leave space for the denominator, and I'm going to just solve for this. So we get 35 minus 8, and then 35 minus 8, we're going to get 27. Okay, now magnitude of vector A is going to be the square root of 5 squared plus 4 squared. Okay, so 5 squared is 25 plus 4 squared is 16. I get the root of 41. And then we're going to multiply that by the magnitude of b squared. So this is going to be 7 squared plus -2 squared. Okay, so 7 squared is 49 plus -2 squared is 4, which is going to be root 53. So if we have root 41 times root 53, this is root 2173. Okay, so let's bring this up here. Now we have cos theta equals, I'm going to divide 27 divided by root 2173, and I get 0.579207, and so on. Okay, we want to solve for theta, so we're going to cos inverse both sides, and we get 55 degrees. So the angle between these two diagonals is 55 degrees. So one of the most important properties of the dot product is its applications to determining a perpendicular vector to two given vectors. Okay, so example 5 is just this. Find a vector or vectors perpendicular to each of vector A and vector B. So what we're trying to find is find a vector in the form x1, y1, z1. So if you think about, and let's call this just vector C. That's fine. Okay, so if you think about A dot C, what's going to happen is we're going to have vector A, which is 1, 5, -1, and we're going to dot it by x1, y1, and z1. And that's going to equal 0. Okay, in other words, actually, I'm going to drop the ones. So I'm going to have x plus 5y minus z equals 0. Okay, so now vector B dot vector C is going to be the same thing. -3, 1, 2. So we get -3, 1, 2 dot C, which is going to be x, y, z. And when we multiply them, we're going to go -3x plus y plus 2z, and this is also going to equate to 0. Okay, so we have two equations here, but the issue is we have 3 unknowns because this is an r cubed, but that's okay. I'm going to teach you guys how to introduce a parameter. So we're going to set these up in a matrix. What that is instead of using the x's and the y's, and it gets really, really confusing and messy, we're going to simply just use the coefficients. And it's just like elimination. If you remember in grade 10, elimination, substitution, okay, it's just elimination. The only difference is that we're only dealing with the coefficients. We're no longer writing the x, y's, and z's. We'll reintroduce those in the end. Okay, so what is the coefficient of x? Well, it's 1. Then leave a little bit of a space. What's the coefficient of the y? It's 5. Leave a little bit of a space. What's the coefficient of z? -1. Okay, we put a long bar, and it kind of is like the equal sign, and it's going to equal 0. Okay, and stacked on top of that, we go in the same order. What is the coefficient of x? Well, it's -3. The coefficient of y is 1, and the coefficient of z is 2. And this equals 0. So, in other words, this first column represents our x, the second column represents our y, the third column represents our z, okay? Like, well, the a values, it's usually ax plus by plus cz, and then this is going to be our constant, or like our d value. But because we bring it over the equal sign, it's -d. Okay, so here are the rules of matrices. You can multiply, you can add, you can subtract, and divide rows. You cannot multiply by 0. Okay, you can't multiply by a 0 vector. Sorry, I'm going to correct this. We can add and subtract the rows. We can multiply or divide by a constant. Okay, and you can do more than one of these in the same line. So our goal right now, our goal is to get a 0 in this bottom left position. Okay, so what I'm going to do is I'm thinking, how can I get a 0 here? So I'm going to do row 2, right? Because this is row 1, this is row 2. I'm going to do row 2 plus 3 times row 1. Because if I do 3 times row 1, it's going to be, essentially it's going to be 3, 15, -3, and 0. Okay, so I'm not touching row 1. There's no operation applied to row 1. I'm just going to rewrite it. And now row 2, so I have -3 plus 3 is 0. That's our goal. Okay, so now we just have to see what the x, y, and constant values are. So I'm going to have 1 plus 3 times row 1. So 1 plus 15 is 16. So now we have 2 plus 3 times -1, which is -3. So 2 plus -3, I get -1. And then 0 plus any multiple of 0 is just going to give us 0. Okay, so because we've achieved this 0 in the bottom left-hand corner, what we can do is we can rewrite these two as actual equations. So the first equation is going to be just as it is, because we didn't change that. It's going to be x plus 5y minus z equals 0. And the second equation is going to be our 16y minus z equals 0. So what we want to do is we want to sub 1 equation into the other. So let's go ahead and bring over this z, and we get 16y equals z. So what we can do is we can sub this into the first equation. Okay, so x plus 5y minus, okay, z is equivalent to 16y, okay, and we get equals 0. So we get y minus, so what's 5 minus 16 is negative 11y. Okay, so x, I think I said y, x. So x equals 11y. Okay, and we have z equals 16y. So this one's going to be a little bit different. We're not able to solve for an x, a y, and a z. And the reason is because we have 3 unknowns, but only 2 equations. So what ends up happening is we have to introduce a parameter. Okay, let me change color. So introduce something called a parameter. I'm going to introduce the parameter t. So if we're thinking that we have a solution x, y, z, but we can actually express this entire solution in terms of y, because both of these equations have a y in it. So x is going to be 11y. So instead of x, we're going to write 11y. And instead of z, we're going to write 16y. So this equation is going to be perpendicular to both of our original vectors. So using the parameter t, we're actually going to say 11t, comma, t, comma, 16t is going to be perpendicular to both vectors a and b. Okay, and what does this parameter mean? So what this parameter means is that for any value such that t does not equal 0, right? We're not going to substitute a 0 in. It's just going to give us a 0 vector. Okay, so for any value which t does not equal 0, we can sub in into like this vector, because the vectors extend in both directions or in all directions forever. Because vectors extend in all directions infinitely. Okay, so all this means is that, for example, if we had like a 2D vector, just to make this simple, if we had a 2D vector like this, if we multiplied this by 2, we would just have double the length, right? So it's kind of like the same idea where we're subbing in a parameter for value t. We're just going to get a duplicate of this vector. So a quick example is if t equals 1, then our vector is going to be 11, 1, 16. We can also check this vector to make sure that it is perpendicular to both equations. Okay, because we have these 2 equations here, we can take both of these equations, because these are already the dot product equations, x plus 5y minus z. So if we take this over here and we do x plus 5y minus z equals 0, and then we take negative 3x plus y plus 2z equals 0, and we sub in our vector that's perpendicular, which we know is 11, 1, 16. Okay, so substitute in 11, substitute in 1, substitute in 16, and we solve for this. We do get 0 equals 0. So 11, 1, 16 is perpendicular to our first vector. Now, if we do negative 3 times 11 plus 1 plus 2 times 16 equals 0, again, we're going to get 0 equals 0. So 11, 1, 16 is perpendicular to our second vector. And if we took even a multiple of this, so say we did like the parameter t equals 2, we're going to get the vector 22, 2, 32. Okay? Or the parameter 3, we're going to get something else. No matter what, when you sub these in to both of these equations, you're going to yield the answer 0. It's going to be perpendicular because these, like this one and this vector, are just multiples of each other.